Now we're going to start talking about some of the techniques we can use to integrate more complicated functions. So just like we needed to have rules, the chain rule, the quotient rule, the power rule, or the product rule, etc., to derive more complex functions, to integrate more complex functions, we need a series of techniques. The first of those is going to be integration with substitution. So here's the concept that we're going to work with. So it's the reverse of the chain rule in derivations. So just like in derivatives we have the chain rule, we're going to do the reverse of that to get integration with substitution. So you start, kind of to prove this, we're going to start by writing the chain rule and integrate both sides. So if we integrate this left-hand side, and we integrate this right-hand side, what do we get? Well, by the fundamental theorem of calculus, we know that if we if we take the derivative of something and then we integrate it, they kind of cancel each other out. So we get f of g of x plus c is equal to the integral of f prime of g of x times g prime of x dx. So you'll notice if you have something that looks like this on the right-hand side, f prime g of x, g prime of x, we can work backwards. But more commonly you're going to see it written in terms of not derivatives, but in terms of integrals. So we can write that. Let me make sure I have all the stuff to fill in for you. More commonly, you'll see it written as the integral of f of x, or f of g of x, sorry, is equal to f of g of x plus c. So in other words, writing it in terms of the antiderivative of f rather than thinking about f in here as being a derivative. Or if you used the kind of rules that were presented above, if u equals g of x and f is integratable, we can write it as the integral of f of u, u prime du is, or sorry, f, that's not right. It should be like this. F of u du equals big F of u plus c, which is also equal to f big F of g of x plus c. This is I know this is kind of ambiguous and unclear, but once we start doing examples and start playing with it, I think that will clear things up. But this is the concept, this is the underlying expression. So the trick here is to look for a nested function, u of g of x, and then take the derivative. And then we just kind of work through. So for example, sorry, I have to scroll my notes over here. If we look here, we've got this function right here that's kind of nested because we've got the fifth power. So we're going to call u equals, we'll say g of x, and you can use g of x, you can use u, it doesn't matter, it's up to you, equals 1 plus 2x cubed. I prefer using u because then I can say du by dx is equal to, what's the derivative of this? It's going to be 0 plus 6x. So in other words, if I rearrange this algebraically, I can get that dx is equal to du over 6x, sorry, it should be 6x squared. So what did I do? I just found my u. I tried picking out a u of u equals 1 plus 2x cubed. Then I took the derivative, du by dx equals 6x squared. Then I just moved the dx out of the denominator, treat it like a variable. I moved that to the other side. I moved the 6x squared onto the left-hand side. And that's where I get dx is equal to du divided by 6x squared. Now let's plug some things in. I get that the integral of x squared, I can't do anything with that. But remember, this whole expression in the middle here, this 1 plus 2x cubed, I said was u. So I can rewrite that as just a simple u. U to the 5th. And then my dx, we said dx is du over 6x squared. Well, that conveniently cancels out that x squared. And that's because we had said earlier, if this is like our derivative of what's in our kind of nested function, they'll clean up and cancel out. So that, in other words, simplifies to the integral of u to the 5th times 1/6 du. From our properties of integrals, we know we can pull that 1/6 out front. And then we've got u to the 5th du, and then by the reverse power rule, we know that this is going to give us 1 over 6 times 1 over 6 times u to the 6th and plus c. And now all we have to do is go back and plug in our u. So we get 1 over 36 times 1 plus 2x cubed to the 6th plus c. And this is our solution. And if you take the derivative of this, if you want to check, yeah, you can quickly just take the derivative of that and see that you get the same results out. And you can repeat this over and over and over again, plugging in more and more, doing more and more substitutions. As long as you track it, you should have no problem working through this. So in the next video, I'll show you an example of that multiple substitution.